In this first video of 5.1, we're going to take a look at solving inequalities. So first, reminding ourselves of what inequalities are. Inequalities are those symbols that we read greater than or equal to, less than or equal to, greater than or less than. Now, I've grouped them into two separate groupings. This first grouping here, we're calling them inclusive. We call them inclusive because they contain the equal sign with the inequality. So in this first statement, this symbol right here means greater than or equal to when we read from left to right. Greater than or equal to. Here it's less than or equal to. Down here, this grouping of two, we don't call inclusive, we call them exclusive. Okay? Because the statement is that something is simply greater than something else. And when we look at it in that context, it has to be greater than. We don't include the equal part. So it's exclusive of the equal part. Okay, whereas the ones up here were inclusive of the equal part. And then this last one down here, something is simply less than something else. And so it is excluding the equality between the two. The one has to be less than the other. So what we want to remind ourselves is putting this in the context of a mathematical statement that we have to solve for a given variable. So that's what we have right here. I've got negative 2 times 3x plus 5 plus 12 is less than 8. So let's work our way through this and solve for x. I'm going to first start by distributing. That's going to be a negative 6x minus 10, and then a plus 12 is less than 8. Okay, so I took care of the distribution. Now I'm going to combine these two like terms. Negative 10 plus 12 is a 2. So that's negative 6x plus 2 is less than 8. And I'll just keep going with what we know. The simple pieces, subtract 2, subtract 2. That's a negative 6x is less than 6. Last step here to solve for x is to divide the negative 6 away. Now, here is the one difference between solving an equation and solving what we have here, an inequality. Whenever you multiply or divide both sides by a negative number, the direction of the sign switches. So instead of reading x is less than, it's going to read x is greater than, and then 6 over negative 6 is a negative 1. So again, anytime you multiply or divide by a negative, you've got to switch the direction of the sign. So we end up with our solution of x is greater than negative 1. Now, interestingly enough, that is a set of infinite solutions because there's an infinite set of numbers, x, that are greater than negative 1. You can never stop putting together a list of numbers that are greater than negative 1. There's always more. So what we want to do is, since our solution set is a set of infinite numbers, we want to plot that on a number line. So I'm going to put 0, negative 1, negative 2, negative 3. I'll put a 1, a 2, a 3 here. You can start your number line wherever you need to in order to fit the inequality. So first I'm going to go to this negative 1, and I'm going to draw a circle at the negative 1. And then I'm going to ask myself, is it inclusive or exclusive? It does not have the equal part, so it is exclusive. Okay? What that means is I keep the circle open. Everything is going to be x is greater than negative 1, but not including negative 1, so I'm not going to fill it in. If it were inclusive, if it had the equal sign, I would fill in the circle to indicate that we include negative 1 as a solution. However, here, negative 1 is not a solution. The only solutions are x values greater than negative 1. So what I'm going to do from here is I'm going to draw an arrow indicating the direction of x being greater than -1. And we know greater than on a number line is to the right. So this number line chart shows us x greater than -1. And this represents the solution. Both of these combined, we want to see both of those presentations, the solution to this inequality. So in other words, only values of x that are greater than -1. So I can only plug values greater than -1 in for this x value if I expect this entire inequality to be true. Any value less than -1 will produce something that's not true in that equation. So what we now want to do is extend this idea of an inequality to equations that aren't linear. What we have here is an exponential inequality. Now, reminding ourselves, exponential implies that the variable is the exponent, and that's what I have in this situation. The variable x is in the exponent location. So we solve this as normal. We're going to subtract 2 from both sides. That gives me a -3 times 4 to the x minus 5 is greater than or equal to, that's going to end up being a -94. Now, I see this -3 times 4 to the x minus 5, so I'm going to divide the -3 away. That leaves me with 4 to the x minus 5 is, we got to be careful here, we just divided by a negative, which means we switch the direction of our inequality. Instead of greater than or equal, we are now less than or equal. And -94 divided by -3 ends up giving us a 31.33. Good. Okay, so here's the part at which we remember when we solved exponential equations that we had to convert from exponential form into logarithmic form. So here's that conversion piece where we go from exponential to logarithmic form. Now, we learned that we can start by simply going with the exponent. So the x minus 5. Now, I'm going to do my less than or equal, but there's a reason why I'm doing it the specific way. We'll come back to that in a moment. But we do x minus 5 is less than or equal to the log base 4 of 31.33. So we know that that's how we convert from exponential to logarithmic form. The key is when you convert, did we keep the inequality sign the right way? Here's the key to telling whether or not you kept the inequality sign the right way. If we look at it in exponential form, we notice that the value of x is on the less than side of the inequality. After converting, if the value of x still remains on the less than or equal side, we know we've done it correctly. Okay? So, as you convert from one to another, we have to make sure that the variable stays on the same side of the inequality as it was before. So now what I can do is I can go through in my calculator, I can find the log base 4 of 31.33. And when I do that, I get a 2.48. So I've got x minus 5 is less than or equal to 2.48. My last step to solve for x is I have to add 5 to both sides. So I end up with x is less than or equal to 7.48. So what we're saying is the only values that make this statement right here true are values of x that are less than or equal to 7.48. So let's put that on a number line. I'm going to start here at a 3, 4, 5, 6, 7, 8, 9. Notice I constructed it, my number line, to fit where I know my inequality exists. So x is less than or equal to 7.48. I'm going to go to somewhere really close to 7.48, And because it has the equal sign, it's inclusive, so I fill in my circle, and it says that x is less than. So that means my arrow goes to the left. So there we go. We now have a situation where we've solved for and graphed the solution to our inequality, our exponential inequality. So we've looked at linear and we've looked at exponential. We've got two more that we want to look at, logarithmic, and then the final example is going to be radical. Now, logarithmic and radical, we've got to be really careful with because of what we're going to call domain issues. We're going to solve this as normal, and then I'm going to show you what the domain issues are with logarithmic, and then we'll do the same with the radical. So, because the 5 is not in parentheses with the 2x, I know that the 5 is not a part of the logarithm. So I'm going to subtract 5 from both sides. That gives me 4 times the log base 3 of 2x is less than or equal to, let's see, 34 minus 5 is 29. And then the 4 in front here I can divide because it's being multiplied by the log. So divide by 4, that's the log base 3 of 2x is less than or equal to, see, 29 divided by 4 is going to be a 7.25. Great. Now this is the point at which we have to remind ourselves again of converting between log and exponential form. So there's that conversion if we need it, or we simply remember that we always start with a piece inside the log. For us, that's the 2x right here. So I'm going to start with 2x, and just like exponential, the 2x is on the less than side of my inequality, so that's where I'm going to keep it. I'm going to keep it on the less than side of the inequality. So 2x is less than or equal to 3 to the power of 7.25. So we've converted from one form to another. Now what I need to do is I need to figure out what 3 to the power of 7.25 is. So I end up with 2x is less than or equal to 2,878.25, rounded to 2 decimal places. Last step, I'm going to divide both sides by 2, and I get that x is less than or equal to 1,439.13. So here's the solution to my logarithmic inequality. Okay. What I want to now do is I want to put this on the number line. Now, before I do that, here's what I need to do. I need to not only concern myself with the solution, but I need to concern myself with the domain of a function. Now, here's what you always have to remember with a logarithmic equation or a logarithmic inequality specifically, is this: can you take the log of a negative? And as we've seen in a lot of other examples that we've done in previous homework packets, no, we can't take the log of a negative. We've tried in the past to maybe do the log base 3 of negative 4.5. If you do that, what you'll find is your calculator can't do it because taking the log of a negative number is impossible. It's outside the domain of a logarithm. So what we know is we have to have a number greater than or equal to 0, or rather greater than 0, because you can't even take the log of 0. It has to be greater than 0. So whatever is inside the logarithm, for us, that's the 2x. The 2x is the piece next to the logarithm. That 2x must be greater than 0. Otherwise, you cannot evaluate the logarithm. So I'm going to simply solve this for x by dividing by 2, and I get x is greater than, well, 0 over 2 is 0. So here's the reason I did that. I cannot plug any value of x into this equation that's less than 0. X has to be greater than 0, otherwise you end up with a negative in the logarithm. What we have to do is consider this domain restriction in conjunction with this solution that we got. So we notice that the solution says x is less than or equal to 1439.13. Here's the issue. Are there numbers less than 1439.13 that are also less than 0? And the answer is yes, but because of domain issues, we're not allowed to be less than 0. So here's how I'm going to do it on the number line. Because these two numbers are so far apart, here's how I'm going to work it out. I'm simply going to put a 0 here, and I'm going to count by 500s. 0, 500, 1,000, and then 1,500. Now, 1,439 is pretty close to 1,500, so we're just going to estimate. We don't have to get too nitpicky here. We just want to get close enough. So I'm going to put that pretty close to the 1,500 mark because that's where it is. But I know that it says x is less than or equal. So because it's equal, inclusive, we fill this in. Because it's less than, I draw an arrow to the left because x is less than. But this domain restriction says I cannot plug any values in that are negative. So I have to know that x is greater than 0. So I'm going to put an open circle, exclusive, because it doesn't have the equal part. I'm going to put an open circle there, and x is greater than is to the right. So what you can see here is this. Only numbers between 0 and 1,439 will work in this logarithm. Anything less than 0 or anything greater than 1,439 will not work in the given logarithmic inequality. So we always have to be paying attention to the domain issues of a logarithm. Linear and exponentials, they don't have domain issues, but logarithms do, and so does the next type of equation that we're going to look at, radical equations. So the last example we want to look at is solving radical inequalities. Radical meaning that the variable x is underneath a square root, or any root. So let's go ahead and solve these as we know how to solve them already. Let's subtract 3 from both sides. That gives us 4 times the square root of 3x minus 10 is less than, let's see, 82 minus 3 is a 79. Okay. Now I'm going to divide both sides by 4. To get rid of that 4 in front of the radical. That's the square root of 3x minus 10 is less than, let's see, the 79 divided by 4 is a 19.75. Now, how do we undo a square root? We square both sides. So that becomes 3x minus 10 is less than, see, 19.75 squared is 390.06. So to finish this off, we're going to add 10 to both sides. So 3x is less than, what is that going to be? That's going to be 400.06. And to finish that off, we have to divide both sides by 3. And that's going to give us x is less than 133.35. So there's the solution to the inequality. Okay. X has to be less than 133.35. However, just like exponential inequalities, with radical inequalities, we have domain issues to be concerned with. So let's talk about those domain issues. We know that if we're looking at a radical, that we cannot consider, when we're only looking at real number solutions, we cannot consider anything that would make the piece under the radical negative. So we have to know that the 3x minus 10, the piece that's underneath the square root, has to be greater than or equal to 0. I can take the square root of 0, and I can take the square root of anything greater than 0. So the 3x minus 10 has to be greater than or equal to 0. So what does that mean about the x? I'm going to add 10 to both sides. 3x is greater than or equal to 10, and I'm going to divide both sides by 3. And I've got x is greater than or equal to 3.33. So we now have two restrictions placed upon our inequality. X has to be less than 133.35, and in order to satisfy any domain issues, x has to be greater than or equal to 3.33. So how would I do that on a number line? I'm going to start right here at 0, and I'm going to count by 20s. 20, 40, 60, 80, 100, 120, 140, and then 160. So what I've done is I've created a number line where I can fit both of these restrictions on it. So x is less than 133. That's a little more than halfway between 120 and 140. So I'm going to put an open circle there because it's exclusive. I'm not including the 133. I'm only including values less than 133.35. So less than implies to the left. Now here the domain restriction says that x has to be greater than or equal to 3.33, otherwise there's a negative under the square root. That's about right here, and it's inclusive, so I'm going to fill it in. Notice again, I'm just estimating where my circles go, getting as close as I can with the number line that I had to use, and x has to be greater than. So connecting these two, we see that the solutions to this radical inequality are all the values of x between 3.33 and 133.35, including the 3.33 but excluding the 133.35. So there's the solution and the visual representation of the solution for the radical inequality, showing the values of x that make this original statement true.